So acquaintance of yours, he comes to visit you at Stanford and he learns that you have been taking a course on semiconductors and he has worked in semiconductors previously, and he considers himself expert in the field. So let's call him a semi-expert, and he wants to test that, can you apply your knowledge of semiconductor devices in real world situations. So he asks you a trick question. So he asks you a question, and he says that hey, I have these three slabs, and he has prepared these three slabs which are identical in shape and size, and he says one of them is a semiconductor, one of them is a metal, and one of them is an insulator. He doesn't tell you which one is what, and he asks you, can you use the knowledge you have learned in this course and design a simple experiment which would tell which one is semiconductor, which one is metal, and which one is insulator. So you ask him, okay, okay, that's a fair question. I think I can, take a crack at it, but I'll need some equipment, and I'll need some maybe a lab to find this out. So how much money do I have to conduct this experiment? So I said, I don't have too much budget, but I can still loan you out. Maybe I can give you $20 to conduct this experiment. So you have to be fairly fairly resourceful to find out how you can conduct this, and tell him within $20 which one is semiconductor, which one is metal, and which one is insulator. So let's go back to something we studied in the course, and let's look at how do the band diagram of a metal compares with that of a semiconductor, compares that with an insulator. So in all cases we have a conduction band. So this is the conduction band for semiconductor, this is the conduction band for metal, and this is the conduction band for insulator. And we also have a valence band, which is separated from the conduction band in the case of a semiconductor by a band gap. And this band gap for a semiconductor is anywhere between 0.5 to 2 volt, or in that range. So let's say it's silicon, so this band gap is 1.1 electron volt. In the case of metal, we have these conduction band and valence band overlapping with each other. So this conduction band is overlapping with the valence band. So this conduction band is already filled with electrons. So this conduction band is already occupied with electrons. In the case of an insulator, you have a large separation between your conduction band and your valence band. So this is your valence band, and this is your conduction band, and they are separated by a band gap which is very large. So let's say we have a band gap of 5 electron volt over here. So in the case of insulator, most of your electrons are located in your valence band, and you have very little or actually no electrons in your conduction band. In the case of your semiconductor, also most of your electrons are located in your valence band, but this band gap is small enough such that at room temperature, or at reasonable temperature, a few of these electrons can gain enough energy such that they can go from this valence band, and now they can go into this conduction band where they are become free electrons. And so most of your electrons are located in your valence band, but you also have a few electrons in your conduction band. So now you think about, what can I do in $20 which will tell me how do I differentiate this metal from the semiconductor to insulator. So you think about the first thing you can vary very easily if you're even at your home is you can vary the temperature. Or, you can place these slabs on top of a hot plate. So you can take a hot plate and place these 3 slabs of materials on a hot plate, and you can vary the temperature of this system. So you can vary the temperature, and that's pretty easy to do. And so then you think what will happen if you vary the temperature in a metal and what would happen if you vary the temperature in a semiconductor, and what would happen if you vary the temperature in the case of an insulator. So let's say you are varying the temperature from room temperature, which is 300 Kelvin, to let's say you are going to up to 100 degrees centigrade or 400 Kelvin. So what would happen in the case of a metal? So in the case of a metal, this conduction band is already occupied with the electron. So now what would happen in the case of a metal is that when you increase your temperature, one thing which can happen is that these electrons will scatter more. So they'll scatter more with the atoms which make up this metal, and they'll also scatter with other electrons which are present in this metal. So this scattering between these electrons would increase, and what would happen as a result of that is that your resistivity of your metal will increase as you increase your temperature from 300 Kelvin to 400 Kelvin. Now what would happen if you had a semiconductor? If you had a semiconductor and you increase your temperature, more of these valence band electrons, they will gain enough thermal energy so that they can now jump over to the conduction band. So the number of electrons in my conduction band will increase substantially. So I'll have a large increase in the number of conduction band electrons. On the other hand, if I think about scattering, the scattering between these electrons will increase as well. But the primary dominant effect is that this number of carriers which are available to conduct, or number of free carriers, this will increase. And if you think about the resistivity, then if number of free carrier increases, the resistivity typically decreases. So the resistivity of my semiconductor will decrease as a function of temperature. So now let's think about what will happen in the case of insulator. In the case of an insulator also, if you increase your temperature, the number of electrons which are available for conduction in your conduction band can increase. But there's a very large barrier that these electrons in the valence band have to overcome to reach the conduction band. So typically what happens is, before this conductivity starts to increase, this conductivity increases because this Ni increases, but it increases at it increases only if you go to very high temperature, and you need a very high temperature to achieve that, and many a time this temperature can exceed the melting point. But for the range in which I am conducting this experiment, that is 300 to 400 Kelvin, that temperature range is not sufficient enough for excite these electrons from the valence band into the conduction band. So for this temperature range, the resistivity of my insulator should more or less remain constant. So my resistivity or the resistance of my insulator should remain same in this temperature range. So now this is interesting. If I increase my temperature from 300 to 400 Kelvin, the resistance of my metal should increase, the resistance of my semiconductor should decrease, and the resistance of my insulator should more or less remain the constant. So what I can do now is, I can go back to my this acquaintance and say, I've figured it out. So what I'll do is I'll place these 3 slabs of semiconductor, or these 3 slabs of material that you gave me, and I'll place them on a hot plate, and I'll vary the temperature from 300 Kelvin to 400 Kelvin, and you have been generous enough to give me this $20. So I'll use this $20 to buy a voltmeter. So let me see if I can buy a voltmeter. So I look up on Amazon, and there are many voltmeters available for very good voltmeters available for less than $20. So I'll buy one of them, and I'll use that to measure the resistance. So I'll use the voltmeter to measure the measure the resistance as a function of temperature. So what I'll do is I'll vary my temperature from 300 Kelvin to 400 Kelvin, and I'll measure my resistance. And let me plot the normalized resistance over here. So I'm plotting versus what I measured at 300 Kelvin. So what I see for material A is that for material A, this resistance, it increases with temperature. In fact, it increases linearly with temperature. So I can say my material A is a metal, and for most metals, my resistivity, essentially it varies linearly with the temperature. And it's sometimes given by this relationship where it varies linearly with increase in temperature. And so I can say my material A is a metal. What I observe for material B, on the other hand, is that my resistivity, it falls exponentially as I increase my temperature. And as we discussed, so this probably indicates that this material is a semiconductor. And for most semiconductor, my resistivity, it falls exponentially with the increase in temperature. So this is my material B, and I've identified as a semiconductor. For my insulator, what I observe is that so I know the remaining remaining material should be insulator. And what I observe for that is that my resistivity, it stays more or less constant in this temperature range. So my material C is further confirmed to be an insulator. So I hope I have satisfied this person, my semiconductor expert acquaintance, and he'll happy that I'm learning about semiconductors in a right way.